What do you think about determinants and areas and, for example, matrix? Do you think have some relationship between them? This question can be solved, can be answered in a simple way, in my opinion, of course. For example, if you take two axes, x and y, for example, and taking two vectors like this one and this one, we can imagine a square formed by the two vectors, and of course, this area of this square, which side is 1, is just 1. It's so easy to understand that. So why this? For example, if you take the matrix M, the identity matrix M 2 by 2, for example, like this one, and of course you can take the determinant of this matrix, that is 1 times 1 minus 0 times 0, and the result is 1. Easy too. And the relationship between this determinant and this square area is very simple, because if we take the two vector columns inside the matrix M, we can understand that these two columns are the same vectors that form that square initially. Okay, so what we can think about, for example, when you take the product between the matrix and the first vector, of course we can take a result, and when we take the product between the matrix and the second one vector, we can take another result, for example, and these vectors are very similar. Okay, and the result is this one. But this is very simple to understand. Maybe we need to take another case, for example, to understand a little bit better this process. Okay, so this product between the matrix and vectors result another vector, for example. In this case, these vectors are the same. That's the thing. Okay, but we can take another example. Okay, for example, if we take the matrix formed by this one 2 by 2, for example, 2 0 and 0 4, and the columns are 2 0 and 0 4 2, and we can take again the determinant of this matrix, but these matrices are different. Okay, so in this case we have 2 times 4 minus 0 times 0, and of course the result here is 8. Okay, so this determinant is 8, but what happens when we take the matrix M, making a product between the first vector and this same matrix, making another product with another vector, for example? And of course these vectors are the same in the first case. The only thing here that changed was the matrix, for example. So when we take the process here of these two products, of course we have another two vectors, and these two vectors are this one, for example, in the first case 0 and 4, in the second case 2 and 0. Okay, but the thing is that when we can imagine these two vectors like this way geometrically, we can put these two vectors in the system. Okay, but the thing is that the two vectors inside the system results for us in a rectangle, and this rectangle have an area. This area is the same of this determinant of this matrix. It's nice, okay, but we have not answered yet, a completely answer yet. The thing is that we can change the matrix, we can make the process between the square 1, which area is 1, and we can understand that this changes the area because changes the vectors that results between the product between the matrix and these first vectors. Okay, so this is the same of the 8 times 1, that is the same, the determinant 8. Okay, so we can understand that the determinant, in other words, can be the product between the first area for the new area. Okay, so but we can understand a little bit better this process. Okay, for example, we can change here the matrix. For example, we can change the matrix here and understand that this matrix is not so similar that the first one, because this matrix is a little bit different. Okay, for example, we can analyze this matrix. This matrix have a determinant, of course, and this determinant is 2 by 1 minus 0 by 1. Okay, in other words, we have here just 2. Okay, so when we take the same process, making the product between the matrix and the first vector, and again make the product between the matrix and the second vector, we can understand that the result here is a little bit different because, let me see, for example, this first result here is 1 and 1, the vector 1 and 1, and the second one is the vector 2 and 0, okay? And why this? What happens here? For example, when we can see these vectors geometrically, we can understand that these vectors are this shape, okay? And just put this shape in the graph geometrically, we can understand that here we have these two vectors. And these two vectors can form a parallelogram, which the area of this parallelogram is 2 times 1. In other words, is 2, that is the new area, times the first area. In other words, again, we have the determinant between this matrix and between making this relationship between this matrix and the first area. Okay, we have here another process like the first two. Okay, so here the determinant is the same. Again, the scale of the new area by the first area of the first vectors. Okay, so we can understand this a little bit better geometrically. For example, when we can change here just to see this square of these two vectors 1 and 0 and 0 and 1, we can understand that this area is just a square, and this square, this area is 1. Okay, but when we can understand the matrix M like algebraically, like A, B, C, and D, for example, we can understand that the determinant is a result that we can call of K. Okay, of course that we have this number is A times D minus B times C. Okay, but here geometrically, to understand that, we need to change or making the same process. For example, just taking this matrix, I know this matrix is just algebraically, but no problem here. And when we make the product of this matrix between these two vectors, again, we have a result, okay? And this result here is completely analog of the same process. These two vectors are two vectors in the system. I don't know the numbers of these two vectors in orange, okay? But these two vectors have a representation like this one. And again, we have a shape here, like this is the parallelogram between these two vectors, and this parallelogram have an area, of course. And this area, guess what, is the same that the determinant. So this determinant is always the same. This determinant is kind of a scale between the first area, that is square with area 1, for the new area, that is the parallelogram in orange here in the system. Okay, so this area is K times 1. But what happens if we have another area, not the first square with area just 1? If we have an area like this one, the completely another area, okay? We have the representation here by two another vectors in green, for example, this 2, 1. These two vectors have the same row, for example, of the first one vectors, 1 and 0 and 0, 1. Of course, this case is not 1 and 0 and 0, 1, but here we have a kind of rectangle that completely shaped this area of this new area in green, okay? So this area is the new area, but again is a new area completely different the first one, that is a square. What happens if we make a product between this matrix by each vector of this case? For example, we have another result, and this result is again another two vectors, for example these two vectors in orange. And when we represent these two vectors in orange here in the same system from the origin, we have again another area, and this another area is completely different than the same one, because these two vectors in orange are different than the first two vectors in green, okay? And this forms here a parallelogram. And here we have another area, and this area represents again the changing of the first area in green for the second area here inside the parallelogram. It's kind of a just changing of bases. For example, here we have a new area inside this parallelogram, and this area is the same that the first one, just multiplying by k, and this k is the same. is the determinant of this matrix. So this is the relationship between the matrix and determinants. We can change again area by area just multiplying by the determinant. So this is geometrically represents what happens this area using the determinants. Again and again we can change in the area depends of these vectors in orange. When we change the vectors in orange, we can change the area multiplying by k. For example, if we have two vectors so similar, we have, for example, an area very small. For example, the determinant is almost 0. If we have an area so much greater than the first one, we have the k so much greater. So the determinant is bigger, okay? So this is the relationship between determinant, matrix, and areas, okay? See you in the next one, guys.